In this video, we'll introduce the conservation of mechanical energy, which is really saying something, or formalize something that we kind of already know. And it just states that in the absence of non-conservative forces, so that would be like friction or like a person pushing something, then the change in kinetic energy plus the change in potential energy of an object is equal to 0 joules. And all that means is that if you gain kinetic energy, you must have lost that much potential energy, and vice versa, right? Because the kind of general conservation of energy holds, so that if you're gaining kinetic energy, well, it had to come from somewhere. If there are no conservative forces around, then it had to come from potential energy. And remember, that's just because conservative forces allow you to store potential energy. And when they do negative work, which means when they are when you transfer energy to them, conservative forces will store that as potential energy and they can give it back to you later, whereas non-conservative forces cannot. And this is kind of nifty because, again, if you had this kind of 1 kilogram ball and it's 10 meters above the ground and you're dropping it, well, you can figure out its potential energy at the top, because we have the change in potential energy is negative work done by gravity, which is negative 1 kilogram times negative 9.81 meters per second squared times 10 meters. So you'll get a positive 98.1 joules. So for potential energy at the ground, 0 joules, then at the top, by lifting it up, it has gained 98.1 joules. And now that we know kind of how much energy it has up here at the top, it's got 98.1 joules of potential energy and 0 joules of kinetic energy. At any point along the way now, if I tell you one, you can tell me the other really quickly, right? So if I tell you right here, when the ball is right here, it has 60 joules of kinetic energy, then you know that the potential energy it has, okay, if it gained 60 joules of potential energy, it must have lost 60 joules of potential energy. So you'd be left with 68.1 joules of potential energy. Oops, I'm sorry. 38.1 joules. And that's because, you know, here the ball will have the same amount of energy. Right now it's split that energy up differently, right? It's converted some of that potential energy to kinetic energy. But the energy, like the total amount of energy, is the same. And that's all the conservation of mechanical energy is saying. You can't just grab random energy out of nowhere. That would be like a non-conservative force coming in. But we're saying there are no non-conservative forces, and you're just letting gravity do its thing. And that means when the ball, right as the ball hits the ground, or right before the ball hits the ground, if it has 0 joules of potential energy, we know it must have 98.1 joules of kinetic energy. Again, just because now from point A, the top, to point B, the bottom, it has now lost 98.1 joules of potential energy, which means it must gain 98.1 joules of kinetic energy. Remember, this only works because the only force acting on the ball is the force of gravity, which is a conservative force. And once we let in a non-conservative force, again, like someone pushing it or wind or anything like that, it will no longer work. If I wanted to just do a calculation to kind of prove this point down here, I could say that the change in potential energy now from point A to B is equal to the negative of the work done by gravity, which is going to be positive 98.1 joules. So now it's lost 98.1 joules of potential energy.